Dude, the paper was glowing for a second there. Like a bit shot out.
Yeah.
That was great.
Now, it's not to say that glow sticks are a particularly safe mixture normally, but I'm pretty sure that this takes the cake as the world's most terrifying glow stick reaction. I've just taken to calling it the glow stick of doom at this point. That red glow comes from a special form of oxygen that is produced in the reaction. But this is way too dangerous for me to do in my lab, so we're going to take a little trip and visit Nile Red. There's actually a small smattering of videos and images of this reaction, but far as I could tell, most of them are recorded with a potato, and I've always wanted to see it in high def. This is a reaction I've wanted to try for a really long time, but the only reason I'm doing it now is because I can use Nile's fume hood, as it's just not safe to do otherwise. So don't attempt this unless you have one, it's not safe to do outside. So what is the reaction? Well, it's actually really simple, and we're going to look at two variants. All you need is concentrated 30% hydrogen peroxide and a source of concentrated hypochlorite, the same stuff that's in household bleach, though that won't work for this. The simplest version is to drop a piece of trichloroisocyanurate into some of the peroxide. On contact with the liquid, the TCC, as we're going to call it, breaks down to form hypochlorite in solution. This is why it's used as a chemical for maintaining pools. It's basically a puck of bleach. This reacts with the peroxide to produce a lot of oxygen, but even though it's still the dioxygen molecule we're familiar with, it's in a special excited state called singlet oxygen, which we'll talk more about in a moment. This state is unstable and highly reactive, and the molecule wants to get rid of that energy and return to being normal oxygen again. In the short time that singlet oxygen is in solution, it can react by bumping into another singlet oxygen molecule. They both release their energy at the same time, which we see as an emission of red light at exactly 632 nanometers. That's why the red color looks so perfectly red. The rest is just released into the air, where it'll last for a few minutes before decaying. One of the many reasons this is super dangerous is because the whole process liberates a pretty large quantity of chlorine gas along with that reactive singlet oxygen. Okay, now for the more advanced method that's also much brighter. For this, we're going to need to really angry up the pixies in the solution, and we had a few spillovers where the reaction just went completely out of control. This time, rather than using TCC to generate the hypochlorite, we're going to use chlorine gas directly. But for this to work, we need to basify the peroxide with pretty concentrated sodium hydroxide. This way, it'll form sodium hypochlorite and then just sodium chloride as the reaction progresses. The way we found worked best was to dissolve some sodium hydroxide in a minimal amount of water, and then to add some peroxide to it. Do this slowly, as there's a threshold amount where the solution suddenly flares up. It'll probably get really angry for a second, but once it dies down, the solution is primed. We notice that the solution looks vaguely bluish in this state. We think that might be because of dissolved oxygen, but we're not actually sure. For the chlorine, we set up a simple chlorine generator that uses crushed TCC tablets and an addition funnel full of 15% hydrochloric acid.